All right, here's problem 17. We want to estimate a population proportion. That's what's being asked of us here. A good way to start estimating a population proportion is to compute the sample proportion. In this case, we had 160 out of 200 students taking an online course. That works out to 80%. So what we can do now is build a distribution centered around 80% that's going to give us an estimate for the population proportion. To do that, we can just go 2 standard deviations each direction. That's giving us roughly a 95% confidence interval. But to do that, we need to know the standard deviation. That'll eventually give us a low and high estimate. More on that later. First, we need to compute how far apart these standard deviation marks are using this formula. Plugging in 80% for p hat and 200 for our sample size gives us about a 2.8% sampling standard deviation in this problem. Now, to get the high estimate, you would just take 80% plus 2.8 plus 2.8. And to get the low estimate, you would do 80% minus 2.8 minus 2.8. Then just summarize in a sentence what it is you calculated, and you're done. Here's problem 18. Here, they're asking us about a future sample that we might take from a certain population compared to yesterday's sample. Since they're asking us what's the probability that tomorrow's sample will have more listeners than the one we got the day before, we have to know the percentage we got the day before. The day before, 15 out of 20 people listened to podcasts. That works out to 75%. So the question is, what is the probability that tomorrow our sample will be higher than 75%? For that, we need a sampling distribution for proportions. And it looks kind of like this. You can see the blue tail as representing the probability of getting a sample that's 75% or higher. But of course, to calculate this, we're going to need normal CDF. But we're also going to need to know the distance between the standard deviation marks, or the sampling standard deviation. Here's the formula for sampling standard deviation. Notice that we have p here, not p hat, which is the population proportion. So p is going to be 60%, and of course our sample size is 20. Plugging all that in gives us approximately an 11% sampling standard deviation. Back to the blue area. The blue area represents the probability that tomorrow's sample will be 75% or higher. To calculate that area, we use normal CDF, of course, using all the typical parameters. Normal CDF gives us about 8.6%, which leads us to the conclusion that there's about an 8.6% chance of getting more podcast listeners than we did yesterday. Here's problem 19. They're asking us about the top 10% of student cyclists in terms of their miles. Whenever a problem is asking about the top 10 or the bottom 15 or the middle 50 or any such thing, you can pretty much be sure you're going to use inverse norm. Here's a distribution showing the top 10%. Remember, inverse norm is, on your calculator anyways, is based on the bottom portion. So if you want to know about the top 10%, you have to consider that it's asking about everyone who's not in the bottom 90%. You can then feed 90% into inverse norm, inserting the population mean and standard deviation, and it will tell you 15.8, representing 15.8 miles. Just so you know, the answer to this problem is not that Jonathan, the student in our problem, rides 15.8 miles. They didn't say where in the top 10% he was, so we would have to say that he rides at least 15.8 miles. Here's problem number 20. They're asking us what percentage of Americans are 64 inches or shorter. This bell curve represents all American heights, and the blue area represents the 64 or shorter. Since we want that percentage, we're going to use normal CDF, plugging in the usual parameters. Normal CDF does all the work, and our conclusion is that 15.9% of Americans are 64 inches or shorter. Here's problem number 21. You'll notice in this problem they're asking us if a certain claim is likely. We might call this a hypothesis testing problem. Regardless of what you call it, the claim is made that a proportion is above 50%. What do we do whenever there's a claim that something is above or below a certain number? We temporarily assume that it is exactly that number. Now, under the assumption that exactly 50% of people carry a water bottle, which we don't know, but we are currently operating under that assumption, we can create a sampling distribution with 50% at the center. And we can see where our sample lies and have some insight into what it might tell us. But before you can look at a sampling distribution, of course, you need to know this distance, the sampling standard deviation. This formula will give that to us. P is the 50% that we are currently assuming own a water bottle. If you do the math on this, it works out to 5%. Now the question is, where does our sample lie? Is it within 2 standard deviations of the mean, or is it beyond 2 standard deviations of the mean? Well, it turns out if you do 50 plus the standard deviation plus the standard deviation again, you get a 60% second standard deviation mark. And how unusual, our sample is 60%. Notice in the problem, 60 out of 100 people did carry a water bottle. So our sample is right on the border between the likely samples and the unusual samples based on our assumption. But what do we do if it's a kind of a wobbler here right on the edge? Well, we could say that this gives us reason to doubt our assumption, but just barely, and that the evidence to support the claim is weak. You could go the other way on this problem and say there's not enough evidence to support the claim. If this were an exam, I would take either one. For no particular reason, it seemed far enough out to me to accept the claim. You might want to take a minute and pause on this. This is how we could summarize all that information into one paragraph. Here's problem 22. They're asking us to assess whether a claim is valid or not. In other words, we're doing a hypothesis testing problem. The claim is that the average water intake is more than 64 ounces. So to analyze that claim, we're going to assume that it's exactly 64 ounces. If it's exactly 64 ounces, we can create a sampling distribution for samples of size 700, as we have in this problem. Of course, we'll need to know the sampling standard deviation, and our usual formula will tell that to us. The sampling standard deviation works out to be approximately 0.8. Well, if I go to my curve, my sampling distribution, I can take 64 and add the sampling standard deviation, and that would be 64.8. But notice our sample average was also 64.8. Our sample is right there. What you can see here is that our sample fell 1 standard deviation above the mean for this sampling distribution. Therefore, it's not particularly rare. It would have to be 2 or more standard deviations away for us to consider it rare. And if it's not particularly rare or unusual, then it's kind of expected, given the assumption. And if that's the case, we have no reason to doubt our assumption that the average water take is exactly 64. And if there's no reason to doubt that assumption, there's no reason to necessarily accept the claim, and the evidence therefore doesn't support it. Take a minute to read this. This is how you might write it out in a nice paragraph. And here's problem number 23. You'll notice in this problem they're asking us to estimate something. You might call this a confidence interval. We have a sample average here of 750 followers based on our 40-person sample. So what we can do is we can build a distribution centered at 750 and use that distribution to get a low and high estimate for the number of Instagram followers. But of course, we can't find those estimates until we know the standard deviation in this bell curve, sometimes referred to as the standard deviation of errors, using this formula. Plugging in what we were given in the problem, doing the math, this normal distribution has a standard deviation of about 31.6. So if I take 750 and I add 31.6 twice, I'll get the high estimate. 750 plus 31.6 plus 31.6 is about 813. I'm rounding to three figures, of course. Likewise, the low estimate comes from taking the 750 and subtracting the standard deviation twice. That works out to about 687, leading us to the conclusion that the number of Instagram followers is somewhere between those two numbers. Here's problem number 24. This problem is talking about a random sample of 300 people, but we're not going to use a sampling distribution on this problem because there's nothing in this problem that asks us about a sample average. Let's continue, and we'll say more about that later. This bell curve represents the population in regard to how much they spend on food delivery. And because the standard deviation is $40, I can take the population mean, 105, and I can subtract 40, and I can add 40, and get those two numbers. Funny thing, those are the two numbers in the problem. So they want to know about the people who spend between $65 and $145 on food delivery. Now, never mind the 300 people for a moment. This blue section represents all the people in the population who spend between those two amounts on food delivery. If we could figure out what percentage of the population that is, it would be fair to assume that that same percentage of our sample might spend that amount on food delivery. So to do that, we're going to use normal CDF using the normal numbers. And what that tells us is that 68% of the population spends between $65 and $145. Here's the logic. If 68% of the population spends that much, it's reasonable to guess, although we can't be sure, but it's reasonable to guess that 68% of our sample would also spend that much. So if you multiply that percentage by the size of the sample, you get a decimal, but it's about 205. And therefore, the conclusion is that we would expect about 205 people to spend that much on food delivery.